I am Georgios Karananas, and I will be discussing about how an underlying conformal symmetry of the Standard Model, which is broken by gravity, can paint a complete and phenomenologically viable picture of our cosmos. The Standard Model is a profoundly successful description of the strong, weak, and electromagnetic interactions of all known elementary particles. Its last missing piece, the Higgs boson, was observed back in 2012. However, what has not been observed are convincing deviations from the Standard Model at particle physics experiments. Moreover, for a Higgs mass of 125 GeV, the theory is a self-consistent, effective description of nature up to very high energies, comparable to the quantum gravity scale, the Planck mass. It is therefore logical to wonder whether we have in our hands the final theory of nature. The answer to this question is negative, and the reasons are compelling. First of all, the Standard Model in astrophysical and cosmological settings, it fails to accommodate well-established observational facts. These are related to the physics of neutrinos, the baryon asymmetry of the universe, and the presence of dark matter. Interestingly, all these can be addressed by the presence of three right-handed neutrinos with masses around the electroweak scale. The next question is about the large-scale homogeneity and isotropy of the universe. Now, it's commonly accepted that this is because of an inflationary epoch in the very early universe, and in what I'm going to be talking about, it is the Standard Model Higgs field that is responsible for that. And finally, there is the question about the present-day accelerated expansion of the universe, which can be attributed either to a cosmological constant or dynamical dark energy. But it is important to stress now that no theory to date exists that is able to predict a value for the cosmological constant or that works out of the box in the case of dynamical dark energy. From the theory side now, the Standard Model suffers from one and only one problem, and this is the presence of Landau poles associated with the U1 and Higgs sectors. But these take place at energies which are well above the Planck mass, and the Standard Model has stopped being a valid description of nature well before this happens. In addition to that, there exist certain fine-tuning issues. One is related to the fact that strong interactions preserve CP symmetry to an incredible accuracy. And this is addressed usually through the Peccei-Quinn mechanism and the associated action field. Now, when gravity enters the game, the situation becomes even more confusing, because there is no explanation for the incredible smallness of the vacuum energy compared to the Planck scale, and the incredible smallness of the weak force compared to the gravitational force. These are the infamous cosmological constant and hierarchy issues. Let me stress that none of the fine-tuning problems of the Standard Model pose a threat to the self-consistency of the theory, but tell us that we still do not have all pieces of the puzzle. To address the hierarchy issue, there have been ingenious proposals. Among them, the ones that stand out are low-energy supersymmetry, compositeness, and large extra dimensions. All of these setups predict distinct experimental signatures right above the electroweak scale, and this is something that differentiates them significantly from the Standard Model. Now, as I've already said, no convincing deviations have been observed at particle physics experiments. It seems to me, therefore, that it is timely to entertain conceptually different approaches, and one such idea assumes that there are actually no new particles between the electroweak and Planck scales, and also puts at use the fact that nature shows a tendency towards being liberated from scales. And by that I mean the following. If we look at the cosmic microwave background radiation, we see that the spectrum is scale invariant to a very high accuracy. And since this is directly linked to the inflationary dynamics, to construct a field theoretical model that is able to give this sort of predictions is, to say the least, a formidable task. But even forgetting about cosmology and gravity and so on, and looking at the Standard Model, we notice that classically the theory contains one dimensionful parameter, and this is the Higgs mass. In its absence, therefore, the theory becomes scale and conformally invariant. So, could it be that conformal symmetry plays a fundamental role in particle physics? Now, when this symmetry is exact, it has some peculiar implications. First of all, provided that the Lagrangian description exists, then no dimensionful parameters can appear. In addition, there is no particle interpretation in conformal field theories, because the spectra are continuous. On the other hand, nature has both. So, at first sight, it certainly appears that going down this road might lead us to a dead end. But of course, this is a rather premature conclusion. Because what I'm trying to do here is paint a picture that is phenomenologically viable. And this means that the symmetry needs to be broken in one way or another. And in addition, I want this picture to be complete. And for this to be the case, gravity has to enter the game. It is the mere presence of gravity that breaks the symmetry. This has very important consequences for the primeval universe as well as the late universe. And it can be effectuated in two different ways. Either one takes the conformal standard model, that is the standard model with the Higgs mass set to 0, and couples it to gravity in a maximally brute force manner, that is in a way that the symmetry is explicitly broken. Or one takes the conformal standard model and couples it to gravity in a way that it's maximally compatible with the symmetry, that is, in a Weyl invariant manner. So let's first understand how an almost scale invariant universe would look like. Now, to quantify these words that I'm talking about, we need to construct the theory. And to construct the theory, we need to specify the rules of the game. And these are the following. First of all, I would like the gravitational sector to be at most quadratic in the derivatives of the fields and propagate the massless graviton. The matter sector, I would like it to comprise the conformal standard model. And finally, I would also like to allow for all possible couplings between these two sectors. Okay? The only restriction I'm going to impose is that this happens only through operators of mass dimension not greater than 4. So if I follow the rules of the game, I'm going to end up with something which is naively simple. It has the standard Einstein-Hilbert term, the kinetic and potential term for the Higgs field H that I am taking now for simplicity in the unitary gauge. Here the ellipses stand for the rest of the standard model. And notice that there is also an interaction and direct coupling of the Higgs to the scalar curvature. Okay? This non-minimal coupling is actually very important because despite appearances, it is a kinetic mixing between the Higgs and graviton, and it is in disguise and becomes operative for field values relevant in the early universe. And this is what makes inflation with the Higgs field possible. So, once the dynamics is disentangled and everything is expressed in terms of appropriate variables, okay, what I presented before boils down to a minimally coupled canonical field high, but with a potential that it's exponentially flat. Okay? And an exponentially flat potential translates into exponentially small deviation from the sitter. And an exponentially flat deviation from the sitter means that the potential can sustain slow roll. Now, this we can understand from symmetry arguments as follows. The theory for field values relevant for inflation, it exhibits approximate scale symmetry that it's broken spontaneously. Now, Higgs assumes the role of the pseudo-Goldstone mode, which means that it has an approximate shift symmetry, and this is why its potential is exponentially flat. And an exponentially flat potential gives rise to excellent agreement with observations. Okay? The success of Higgs inflation in this sense is inevitable. So once the height of the potential controlled by the non-minimal coupling C is fixed, that is through CMB normalization to match the amplitude of perturbations, it has a rather large value, then the slope of the potential, which is controlled by kappa and dictates the amount of gravitational waves, is also fixed, and it's equal to 1/6, giving rise to spot-on predictions when it comes to observations. Now, so far so good. We discussed the early universe, but what about the late universe dynamics? Because this gravity-induced conformal symmetry breaking needs to be communicated to the particle physics sector. And not only that's not enough, because this must be done in a fully controllable manner in order to reproduce a hierarchy of scales between the Planck and the Higgs masses, which which spans 17 orders of magnitude. Now, perturbatively, the predicted Higgs mass is off by many, many orders of magnitude. So it is logical again to conjecture if there are some non-perturbative gravitational effects that are operative and are responsible for such a separation of scales. Indeed, such effects exist and relate the Higgs mass to the Planck mass in a rather non-trivial manner. Okay? So you notice here that the separation of scale is controlled by the exponent of this kappa parameter that is fixed from inflationary dynamics. Or let me put it in other words, Higgs mass is a computable derivative quantity. It is intrinsically linked to M Planck through inflation. Okay? Colloquially speaking. Now, to obtain the correct hierarchy, we need to have kappa of the order of 40, okay, roughly speaking. However, we saw before that Higgs inflation fixes kappa to be around 1/6. So, what are we missing here? What didn't we take into account? Well, I have been sort of purposefully cavalier as to what gravity I was talking about, or better say, which formulation of gravity I was talking about. And let me be very clear here. I'm not talking about modified gravity. I'm simply asking a very basic question. How should we describe gravitational interaction? Should we only use the metric? Should we use the metric and independent connection? Should we follow the gauge approach? And so on. And the question that you should be asking me is whether this really matters. Okay? And the answer to this question is it depends. And it depends crucially on whether matter is absent or present. Because if a gravitational sector propagates only the massless graviton and no matter is present, then all the formulations are completely equivalent. Or to put differently, GR is the attractor in this landscape of formulations. Now, when matter is present, the above are not equivalent anymore. This degeneracy is completely lifted. So, in what follows, I will be focusing on Einstein-Cartan gravity, because this is the gauge theory of gravity and gets as close as possible to the particle physics perspective. Okay? Remember, gravity, after all, is the quantum field theory of graviton. And just like the mediators for the strong, weak, and electromagnetic interactions emerge by gauging the global SU3 cross SU2 cross U1 symmetry, the gravitational interaction emerges by gauging the global Poincare invariance which is already present in the Standard Model. Now, to achieve that, it is necessary to introduce gauge fields, the tetrad to account for local translations and the connection to account for local Lorentz transformations. Their corresponding field strengths are the well-known torsion tensor and curvature tensor. Now, it is very instructive to understand how one constructs a gravitational sector that propagates a massless spin-to field in this context. Okay? So the logic is to start by writing all possible terms which contain up to 2 derivatives of the fields. Turns out that there are 10 of them. Okay? It's quite a number of terms, and schematically the action reads like that. It contains the cosmological constant, the scalar and pseudoscalar curvature invariance, as well as various terms that depend only on torsion. Appearances are quite deceiving, okay? Because in this action, the connection, and for what matters, torsion, because it's the same, is not dynamical, okay? This can become crystal clear by obtaining the so-called equivalent metric theory. So, vary the action with respect to the connection, solve its equation of motion, which turns out to be algebraic, and gives the well-known relation between omega and derivatives of the tetrad, and upon plugging it back into the action, one ends up with Einstein-Hilbert action, nothing more. Now, when matter fields are present, the logic is roughly the same, simply there are more ingredients. Now, the consequences are not the same. Let's start by discussing how the interaction of the Higgs changes, okay, compared to metrical gravity. So the gravitational sector still will comprise the 10 terms we saw before, but now the rules of the game dictate that I allow for all possible couplings between the Higgs and the gravitational invariance, okay? Now, again, the principle underlying the success of the inflationary dynamics is still there, and this is the approximate scale and shift symmetry. Okay? The predictions are still universal, no need for model building, and so on. However, there is an important difference. Kappa, the parameter that controls the slope of the potential, now does not depend only on psi, but rather is a non-trivial combination, a non-trivial function of all the non-minimal couplings that appear in the theory. And what it means? It means that since the slope is controlled by this parameter, also so does the production of gravitational waves produced during inflation. Now, remembering that the scale separation is again controlled by the exact same parameter, this translates into a prediction of the amount of inflationary gravitational waves and vice versa. And this correlates seemingly uncorrelated phenomena, one that it's primordial and the other that it's in the late universe. So, let's now take a closer look at the Einstein-Cartan dynamics. What we will see is that in principle, this theory is able to propagate extra degrees of freedom which are of gravitational origin and are associated with independent connection. Okay, and this might be relevant and interesting for particle physics. However, there is a catch, a very important problem. It is well known that not all of these particles are healthy. Actually, most of them are not healthy, okay, and lead to pathologies in the theory. Whether or not this is actually a problem, it's an open question, okay? But in any case, here I want to be maximally conservative. So I will focus on one of a very few subclasses which is healthy, and in addition to the massless graviton, it propagates only an extra pseudoscalar. Let's call it A. The reason I'm interested in that is because this guy may be relevant for the strong CP problem. And I'm not saying that out of the blue. The reason this might be the case is the following. Just like the Higgs, also the fermions, when are embedded into the Einstein-Cartan framework, their interactions with gravity changes, okay? It's modified. And the reason is that the covariant derivative contains the full connection, the full independent connection. And now the connection propagates a pseudoscalar mode, okay? So this axion-like particle, this gravitational axion, let's call it for the time being, it's automatically coupled derivatively to the axial fermionic current. So upon integrating by parts this guy and using the fact that A nu is anomalous, the chiral current is anomalous, one sees that A couples to QCD as well as to fermions, so through the anomaly it can get a potential, okay? And this would mean that the strong CP problem is solved gravitationally, or to put differently, that gravity has an inherent mechanism to relax the theta angle to zero, okay? That would be very interesting, that would be actually fantastic, but it turns out, upon further scrutiny, which we showed in a recent article, that interestingly, we just, a few days ago we heard it's now accepted in physical review letters. This does not go through, okay? So, if A appears in the action through derivatives only, like it happens in some sort of more exotic setups, no potential for the field can be generated. There is no effect that can break its shift symmetry, perturbative or non-perturbative. And don't be fooled by the fact that it couples to both these guys. It's very important to realize that this, using the anomaly, etc., it's simply a change of basis. Okay? And physics does not depend on the change of basis. And one can see that no potential is generated for the field by computing, say, the two-point function. And what one will find is that all non-derivative interactions cancel each other out. Okay? And the reason is that the coefficients here between these two guys are fixed. They come from the anomaly and they interfere destructively. Now, in the approach I'm advocating here, this pseudoscalar does not appear or does not enter through derivatives only. Okay? So in principle, a potential can be generated via loops. Okay? Like for instance, the graphs I've plotted, I've put here. Okay? Through fermion loops, one may generate a potential for the pseudoscalar. However, it turns out that the corrections are either unrealistically weak or need severe fine-tunings. Okay, and that would make this action an extremely bad quality action. So, should we give up on this idea completely? It turns out that there is a possible way out, and probably it's the only way out, and Weil symmetry plays a very important role for this to be the case. But first things first, I need to set the stage briefly and understand what we're talking about. Now, if we take Einstein-Cartan gravity and require that it be also invariant under gauge dilatation, there is a unique structure that stands out. And this comprises two terms, the square of the scalar curvature and the square of the pseudoscalar curvature. Okay? So apart from being aesthetically pleasing, because instead of 10 terms we now get 2, or better say, okay, there is also a cross term, so strictly speaking there are 3 terms, there is a cross term between the scalar and the pseudoscalar curvature, but nothing changes in the discussion. Okay? On top of that, this is an action which is ghost-free for all choices of parameters. Okay? Now, these guys, f and tilde f, that multiply the curvature invariance, are the gauge couplings of the Lorentz group. The first one, f, has a dual role. It's the one that controls the cosmological constant, the value of the cosmological constant, as well as the 3-level gravity-induced mass for the Higgs. The other coupling, f tilde, is what controls the action-like particle mass, the pseudoscalar mass. Okay? Of course, we do not pretend that the theory predicts the values. This almost goes without saying that this is the case, that this is not the case, because this is a phenomenological input. Okay? Nevertheless, the theory has some interesting predictions, quote unquote, simply by consistency. First of all, the cosmological constant cannot vanish. This theory makes sense only on spacetimes with non-vanishing curvature. And also, the mass for the action cannot vanish. F tilde cannot be equal to 0. And interestingly, it turns out that the latter is an absolutely essential requirement for the phenomenological viability of this setup, as we saw in an upcoming article with Misha Saposnikov and Sebastian Zell. Now, what are the consequences? First of all, about the strong CP problem and its fate in this context. Now, requiring that Weil symmetry is preserved at quantum level, and remembering that we're talking about a non-normalizable theory, induces novel interactions between axion, between this pseudoscalar with glue, as well as with the quarks. Okay? And very importantly, the coefficients of these guys are uncorrelated. Okay? And therefore, a potential for the field is generated, it fills the theta angle, and thus the strong CP problem can in principle be addressed in the Weil invariant Einstein-Cartan gravity. In addition to that, as we showed a couple of days ago, we posted the paper on arXiv, Higgs inflation is operative, and of course the predictions are in excellent agreement with the Planck and bicep data. The Higgs mass continues being a computable quantity in this context, and now an added bonus is that all the fine-tuning problems are rooted to the gauge couplings of gravity. Okay? And remembering that gravity is after all the weakest force, these couplings are expected to be very, very small. Okay? And let me reiterate what I said before, their values cannot be predicted in this framework, but they're a phenomenological input. Now, actually, I've reached my recap, and I talked how conformal symmetry may be the key for the harmonic symbiosis of gravity and the Standard Model. If inflation is the mechanism that is responsible for the isotropy and homogeneity of our universe, then it is the Higgs field that is responsible for inflation. Gravity has the central role, not only breaks the symmetry, but also communicates this breaking to the Standard Model. Now, if one works in the context of the Einstein-Cartan formulation, one gets as close as possible to the particle physicist's mindset. And moreover, one is able to bridge early and late universe dynamics, the Higgs mass with the production of primordial gravitational waves. Now, Weil invariance happens to be even more interesting in this context. Even leaving aside this aesthetics about number of terms, etc., it has an axion-like particle which is built in the theory. Really, now we have a mechanism which is an alternative to the Peccei-Quinn construction that can in principle address the strong CP issue. And moreover, the cosmological constant, the three-level Higgs mass and the three-level Alp mass are all related to the gauge couplings of the gravitational Lorentz group. Since what I've talked about is literally the tip of the iceberg, there are many open problems and future directions. Just to name a few, for cosmology, it would be very interesting to understand what is this gravitational action's behavior in the early universe. Okay, for instance, it's how much does it contribute to the perturbation budget, if it produces isocurvature modes and so on, if it can play the role of dark matter. This we are addressing currently and we hope to have the answers soon. On the theoretical side, there are quite a number of things that remain to be understood. First of all, what happens with the Weyl anomaly in this framework? Then, the theory is non-normalizable. What is the range of validity? What is an appropriate ultraviolet completion? Now, Einstein-Cartan gravity is also interesting because it has built in the Euclidean continuation. It's rather organic, this thing. So could it be that the path integral is well defined here, the gravitational path integral? Now, for the very attentive listener, I mentioned three right-handed neutrinos needed to explain the real problems, observational discrepancies of the standard model. And these are the right-handed neutrinos. In the Weyl invariant context, these necessarily have 0 three-level masses. This makes them computable quantities, and this can in principle be due to some non-perturbative effect a la Nambu-John Lasinio. And finally, one can even do some model building. For instance, instead of Weyl symmetry, one can require that the theory be invariant, say, under global scale transformations. All the attractive features of the Weyl invariant cousin will remain, but now the spectrum will contain a dynamical dilaton. And this can presumably play an important role in the present-day universe by assuming the role of dynamical dark energy. Thank you for your attention.